Hi, everyone. William Ainsworth,
Here.
say that again, Will.
Oh,
Ah,
here.
Caleb, tell me your microphone doesn't work. I saw you before. Didn't I see him before?
Mhm.
Um, Brody,
Yeah, I'm here.
Joe, Bevilacqua, Joe Blakely.
Yeah, I'm here.
Are you in England or are you in,
No, I'm not in England now. I'm at Bonaventure.
Morgan Brady? Ryan?
Here. Here.
Thank you. Drake?
Here.
Charles? DePasquale?
Here.
Martin?
Right here.
Dejour?
Here.
Bobby?
Here.
Galen? Usse?
Here.
Owen?
Here, I got Shane with me today too. His laptop's not working.
Alex Holden?
Yep. Here.
James Johnson?
Here.
Brooke?
Here.
John Kenny? Jack Kenny?
Here.
Elias?
Here.
Matt Lehman?
Here.
Mike Mandola? Paige?
Here.
Matt Morgan?
Here.
Brandon?
Here.
Connor?
Here.
Matt?
Here.
Shane? Jesse? Ryan? Full?
Here.
Joya? Marco?
Here.
Grace?
Here.
Nick?
Here.
Carrie?
Here.
Chris Starkweather? David? Steria?
Here.
Nolan?
Here.
Sean?
Here.
How is everybody?
Good. Good. How are you?
I don't like waiting until 2:30 to teach. Nobody cares. And I'm freaking hot. How did everybody make out looking at R and stuff like that? Did you try?
A little bit, but I didn't get too far. It was all right. Just
Was
looked at it
okay?
pretty much. Yeah.
Are the data sets in the textbook that you want us to use? Like for the data that we actually plug into RStudio, is that information in the textbook?
It's on the Student Companion's website.
Okay.
Remember?
Yeah, I forgot, but I remember now.
I think there's a link on Moodle to this textbook Student Companion website, and that's where the data sets are. You should download them to your computer and put them in a place where, you know, you'll be able to remember, oh yeah, and you have to write the code for the location of where they are. Cool. Okay, so today is going to be hard because I want to lecture something. It's a math review. I want to start a little math review. Yeah. And it's going to be hard because, you know, I can only speak. Normally I would write on the board, and I like to write on the board and draw pictures. I'm a very visual learner, so I'm a very visual teacher. So I write this stuff down, and, you know, we don't have that facility right now. So we're going to do the best we can, and we're going to suffer through it. I mean, hey, is anybody good at telling jokes? Okay. Can you guys hear me okay?
Yeah.
Yeah, I can hear you fine.
Okay, so this is taken from this book. It's by Chris Brooks, Introductory Econometrics for Finance, 3rd edition. I used this book to teach this course several years ago. And this chapter 2 is just a math review. So you notice there are 60 slides here. You're not gonna need to know everything. But I like this review because it's fairly comprehensive. And anyway, all the slides are there, although you don't have to know them all. So, and it starts out very elementary, and many of you will be like, oh man, I can't believe Gallagher is trying to teach this stuff. This is so boring, you know? I'm sorry about that. And just try and bear with us, okay? So we start talking about functions, just a mapping of a relationship between an input or a set of inputs and an output. In other words, you know, sales is a function of advertising, you know, something like that, right? Y is a function of X or F of X, right? So Y is a function of X. Y could be linear, or it could be a nonlinear relationship. If the equation is linear, we write that relationship as Y is equal to A plus BX. So this is no different than what you probably are more familiar with is something like Y is equal to MX plus B, yeah, where M is the slope and B is the intercept. In this format, we're just saying that B is the slope or the gradient, A is the intercept. okay? X and Y are called variables, and A and B are the parameters. So A is the intercept and B is the slope or the gradient. This is excellent fodder for true, false, multiple choice questions, right? Pain in the ass stuff. So the intercept is the point at which a line crosses the y-axis. You are modeling a relationship between your average grade and the number of hours you studied, right? So y is your grade. Y is a function of how much you study, believe it or not. The relationship can be written as a linear function. Y is equal to A plus BX, yeah? Intercept A and slope is 0.05. So this means that with no study, where X is equal to 0, the student could expect to earn a mark of 25%. That makes sense, right? If you don't study at all, you're not going to do well. And then for every hour of study, the grade would improve by only 0.05%. So if you studied an additional 100 hours, you would have a 5% increase in your grade. It was very encouraging, this, right? So here's a plot of that relationship in that line, yeah? So in the graph above, that slope is positive. Yeah, we can see that. Other examples, the slope could be negative or 0. A straight line, the slope is the same, right? A straight line. In general, we calculate the slope of a straight line by taking any 2 points on the line and divide the change in y by the change in x, right? The rise over the run, delta, this little gizmo here denotes the change. So take 2 points, x is 100 and y is 30. And then another point, x is 1,000 and y is 75. And you can write those coordinates like this, as if you were graphing. And the slope is the change in y over the change in x. In other words, the rise over the run, yeah? Where the change in y is your rise. So the slope of this is 0.05. So calculating roots, this is just the point at which a line crosses x-axis. The straight line will have one root, except for a horizontal line, which doesn't have any roots. So find the root of an equation, set y to 0, and rearrange it. So the root is x equal to negative 500. In this case, this does not make any sense. Number of hours studied required to obtain a mark of 0. It's nonsensical. Then we have quadratics, right? A linear function, but it's not sufficiently flexible to accurately describe the relationship between two series. You could use a quadratic. So a plus b x plus c x squared, where a, b, and c are the parameters to describe the shape of the function. All we're saying is we have an additional parameter compared to a linear function. The linear function is a special case of a quadratic where c is equal to 0. And you can see that if c were 0 here, this term in that equation would drop off. So here what's important, and again, this is fodder for multiple choice or true and false. If C is, and you'll remember this from 7th grade, it's way back there in your brain. If C is positive, the function will be U-shaped. While if C is negative, it will be upside down U-shaped. Yeah? So that's kind of important. All this other stuff is a little bit of noise, but that's kind of important to me. And then, of course, you could have the roots may be distinct. You could either factorize to find the roots or use the quadratic formula. Everybody remembers that from high school, right? Is everybody thinking, why am I here? Don't worry, it gets better. Not much. Okay. So if b squared in that equation is greater than 4ac, two unique roots cross the x-axis in two places. If b squared is equal to 4 times ac, only cross the x-axis in one place. If b squared is less than 4ac, no real roots, complex roots. So then we have this little exercise, right? Determine the roots of the following equations. I'm not gonna ask you to do that because it's really child's play, right? And you all would remember how to do that, and you would all say, Mom and Dad, that money that you're spending for me to go to Bonaventure is being wasted. So we'll just move on, okay? Because I trust that you all know how to do that. Besides, the slides tell you how to do it. Yeah? So this is the first one, the second one. They do that by factorizing formula used, roots. Doesn't factorize, so the formula with A is 1, B is -3, and C is 1. And then we had, this would not factorize in the quadratic. Okay, so this is worth reviewing because nobody ever remembers how to do this, right? Powers of numbers. A number or variable raised to a power is simply a way of writing repeated multiplication. So raising x to the power of 2 means squaring it. Raising x to the power of 3 means cubing it, and so on. So the number we are raising the variable to is called the index. So x to the third is, the index would be 3. Manipulating powers, this is what we all forget. Any number or variable raised to the power of 1 is just that number, right? Any number or variable raised to the power of 0 is equal to 1. These are just the rules. An index is negative, it means we divide 1 by that number. For example, x to the -3 is 1 over x to the 3, yeah? If we want to multiply together a given number raised to more than one power, we add the corresponding exponents. Yeah, so x squared times x cubed is x to the 5th, right? We want to calculate the power of variable raised to a power, right? So x squared raised to 3 would be x to the 6th, okay? So this is not new. This is all child's play, really. We want to divide a variable raised to the power by the same variable raised to another power. You subtract the exponents, right? So x to the 3rd over x squared is x. We want to divide a variable raised to a power by a different variable raised to the same power. That's x over n. X over y raised to the n is x to the n over y to the n. Power of a product is equal to each component raised to that power. For example, x times y raised to 3 is x cubed times y cubed. Powers don't have to be integers. So x raised to the half is a notation we would use for taking the square root of x. Other non-integer powers are also possible, but are harder to do by hand. In general, any x raised to 1 over n is n radical x. Right? And now you remember this. The exponential function e. It's sometimes the case the relationship between two variables is best described by an exponential function. For example, a variable grows or reduces at a rate in proportion to its current value. We write y is equal to x e to the x. E is simply the number, an irrational number, 2.71, blah, 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 blah. It's useful for capturing the increase in the value of an amount of money that is subject to compound interest. Why is that? Surprise, surprise. Now you wish you had a joke to tell, don't you? Why is that?
It's used for continuous compounding.
It is used for continuous compounding. That is exactly right. Why is that? Why do they use E in a financial formula when they're talking about compounding money? So look at, if you brought your money to the bank and they compounded it once a year, you would get, like, say you brought $100 to the bank and they gave you 5%. At the end of that year, you would have $105. Well, if they compounded it twice a year, in 6 months, you would have that $100 raised to 5% for a period of 6 months. But then you would have that new amount raised to 5% for the following 6 months. It's more money, isn't it? At the end of the day, if you had your money raised to 5% every quarter, each quarter, the new amount is raised to the 5%. So it's even more. If you had it raised to 5% every month, it's even more. If they compounded it every day, it's even more. Yeah? So we know that continuously compounded over any considerable length of time is roughly the same as daily compounding. But it is much, much easier to write a financial model using the number E than it is to use like, compound this, 68 over 365 times. Do you know what I'm saying? That's why this is very, very important. And thank you, Matt. Okay. Exponential can never be negative. It crosses the y-axis at 1 and slope goes up at increasing rate from left to right. Here's a picture. Crosses y at 1, it looks just like this, right? Y is equal to e to the x. No big deal. Logarithms, the inverse of of e, right? The natural log is the inverse of e. Logarithms were invented to simplify cumbersome calculations. There are at least 3 reasons why log transforms may be useful. Taking a logarithm can help rescale the data so variance is more constant, which overcomes a common statistical problem known as heteroscedasticity. That's huge, okay? Very important. And I'm going to show you why. Suppose you were modeling some financial data. This is what heteroscedasticity would look like. Can you see that the variance around the mean is quite a lot? It's not constant. If you're modeling financial data and it suffers from heteroscedasticity, you won't be able to trust your estimates of the parameters, the intercept, and the slope. So heteroscedasticity is a real problem. But if you transform financial data into logarithmic data, you eliminate or can eliminate the problem of heteroscedasticity. Do you see the difference? That's a very important feature of using data that you convert to natural logs, okay? Log transforms can help make a positively skewed distribution closer to normal. What does that mean and why is it important? Say, okay, Gallagher, you're the teacher, you tell us. Okay, guys. Can you see that this is very hard to do this? The image on the left is my idea of a normal distribution. The image on the right is my idea of a positively skewed distribution. This is very important. Why is it very important? Look at, we're trying to estimate something. You're trying to estimate this. You want to know what A is, but more importantly, you want to know what B is. When you estimate B, right, you're after the beta of a stock, for example. So that's a regression estimate. You're estimating the slope of a line. You're estimating the relationship between the stock market and a portfolio of stocks that you own. You want to know what the beta is. You estimate that through regression. You convert your data to natural logarithmic data so that you have a normal distribution instead of a positively skewed distribution. Why is that important? Anybody?
I don't know. It's easier to pay attention to like sudden changes in the market.
Thank you, Dejor, but we'll come back to that. Let me help. You run a regression, and it says that the beta is 1.2. In other words, your stock is 1.2 times riskier than the market. You need to test that for significance. Is my face too close to the screen? I don't want you to be able to see outside the back of my head. You want to test those numbers that you estimate for significance so that you can say, the beta on my portfolio is likely to be true. If you don't have a normal distribution, you can't do that. Remember, when you have a normal distribution, you're able to calculate a t-value or a z-score and look it up and say it's true or reject the null hypothesis or accept the null hypothesis. That's why logarithms are so important. Okay? It can also make nonlinear multiplicative relationships linear and additive, as in the rule of logarithms. So here we have how do logs work, right? 2 to the 2 cubed is 8. We will write this as log 2 of 8 is equal to 3. I don't care so much about this, right? This stuff. It can be seen as x increases, y increases. Here's the graph of the log function, right? Y is equal to the natural log of x. Remember when we graphed E, it was like this, right? So this is the inverse of that. Natural logarithms, logs to the base of E, are most commonly used. Natural log denoted interchangeably by ln y or log of y. Taking the natural log is the inverse of taking an exponential. So sometimes we call it the anti-log. The log of a number less than 1 will be negative. So, and you can't take the log if it doesn't exist, a negative number. So here are the laws, right? Natural log of x times y is the natural log of x plus the natural log of y. Remember, we just said converting a multiplicative relationship into an additive one. The natural log of x divided by y is the natural log of x minus y. The natural log of y raised to c is c to the natural log of y. So this is very useful when you're solving for time in a financial equation where you're estimating present value or future value, right? Natural log of 1 is always 0. Natural log of 1 over y is the natural log of 1 minus the natural log of 1 of y, which is simply the negative natural log of y. And then the natural log of e to the x is e times the natural log of x, which is just simply equal to x. So this page, you may want to reference page 22 in the slides, right? Sigma. So you remember this as well. You wish to add together several numbers, sigma notation can be very useful, right? All it means, sigma, means add up all the following elements. Sigma 1 plus 2 plus 3 is equal to 6. Limits. So we may say the sum where I runs from 1 to 4 of x times I. Yeah? This would be adding all the values of x from x1 to x2 to x3 to x4. So it's just a method of notation. And here are the properties, right? So the sum as I runs from 1 to n of x sub I plus the sum as I runs from 1 to n of z sub I is the sum of x sub I plus z sub I, right? And so on, yeah? Okay, pi notation, similar to sigma, except the pi operator is used to denote multiplication. So pi of, as I runs from 1 to n of x sub I is x sub 1 times x sub 2 times x sub 3, and so on, right? And it also would follow that you could pull the C out. Yeah, you can do that. So, okay, differential calculus. What I think we should do, what time is it? 3:05? Page 26. Hang on 1 minute. Let me just look at the book here. Oh, let's do this, okay? How many have a little bit of understanding of calculus? I do this because in my mind, it's important for a finance major at a college, university, to graduate knowing what a derivative is. Yeah? You're not going to know that like the marketing majors or the management majors, right? You know, but it's very important. It's very important because it's a discipline in terms of learning, and it's very elegant. And I just feel that if you're a finance major at any university in America today, you ought to know what a derivative is. So let's talk about this, and then we're going to break into groups and do some problems. So you don't have to listen to me the whole time. The effect of the rate of change on one variable on the rate of change of another is a derivative. The relationship between the two variables can be represented by a curve. The slope of the curve will be that rate of change at any given point. A variable y is a function of another variable x, i.e. y is equal to f of x. The derivative of y with respect to x is dy by dx. Or sometimes f of x, f prime of x. This term measures the instantaneous rate of change of y with respect to x. In other words, the impact of an infinitesimally small change in x. The different notations, change in x and dy. These are not the same thing. What? Notice that there are two ways of saying this. Why are there two notations in calculus? Anybody? It was invented by two different people at the same time, right? Isaac Newton and some other geezer. Leibniz, that's his name. They invented calculus at the same time. What a freaking bunch of geniuses these guys were. Why did they invent calculus? This is why calculus was invented. So this is a castle. These people over here, bunch of people, they wanted to storm the castle. So they used catapults, right? To launch rocks and explosives and stuff onto the castle so that these people didn't shoot them with arrows, right? So they needed to know Well, how fast and how far do we need to launch this explosive device with our, the catapult to get rid of all the people with the shooting arrows at us? You know what I'm saying? Very important. Yeah. So this is how calculus was invented. How fast and how far do we have to shoot this thing? In other words, how do we measure that arc? Okay. So let's go back to here. And we're just going to do some rudimentary things. Derivative of a constant is 0. In other words, if y is equal to 10, the slope of y, or the derivative dy by dx, is equal to 0. Y equal to 10 is simply a horizontal straight line. A linear function is simply its slope. In other words, if y is equal to 3x plus 2, the slope of this is 3, right? Dy by dx, this is a straight line, just runs in one line, right? But nonlinear functions have different gradients at every single point along the curve. The gradient at every single point is equal to the gradient of a tangent line at that point. The gradient will be 0 at the point where the curve changes direction from positive to negative or negative to positive. That's what's important. Let me see what else I got for you. Tangent, so we're just saying, okay, these are the tangents to the curve. Derivative of a power function is, say, y is equal to cx raised to n, is c to the nx raised to n minus 1. Remember that rule from high school if you've had any calculus? In other words, for example, the derivative of y is equal to 4x cubed is going to be 4 times 3, right? The 3 is n minus 1, so 3 minus 1 is 2. This becomes 2. And the 3 comes down here to be multiplied by the 4. So the derivative is 12x2. Yeah? That's the most complicated I'm going to ask you about derivatives, I think. Okay? And I would expect that you would be able to give me the derivative of, 2x to the 6th plus 7 or something, right? Something fairly straightforward. So what I want to do, how many are you? 35, Jesus. Our Moodle is a problem set for chapter 2. There's some circled under number 6, 7, 8, and 9. I'm going to split you into groups, but I want each group to work on all of them. And then we'll come back, okay, and see how you made out and talk about them. As a matter of fact, just do 6 and 7, okay, for today. Just do 6 and 7, and then we'll come back and talk about those. But everybody do them. But do them in your group, and I'll assign groups right now. Isn't this the big surprise is like, who's going to be in my group? So 7 people to a group. Is that cool? Or 5? You want 7 or 5? Nobody knows how to.
7.
Okay. Hi, Ryan.
Hi.
How's everybody?
Good. We're having a little trouble seeing the numbers on the handout. Figure out which ones to do.
What do you mean?
Like on the PDF, it's like you can't really see the numbers to the problems. You can just see like the circled letters.
Oh, really?
Yeah.
Yeah. We kind of just counted down and we were like, we think it's A, B, A, C, D, but I don't know what you want us to do.
All right, let me, okay, just do these. The equations for these lines and the summations.
Okay.
Okay, thanks.
Thank you.
Which one did you say? Same ones we thought. Oh, okay.
Yeah, I want to keep the screen up, but hey guys, just do the first 6 circles, okay? You know what I'm saying?
No.
So yeah, the other groups are complaining that they can't see the numbers on the problems. But
Oh,
they-
so
the circles, right?
we were doing the wrong one then.
Are we supposed to be doing the math problem ones?
'Cause
Yeah.
those weren't listed as numbers, so we thought we had to do chapter 2 problems.
Yeah.
Yeah, that's what we're doing. Chapter 2 problems.
Number 6 and 7, right?
Number 6 and 7, but you can't see the 6 or the 7. You can just see circles.
I can see the numbers on my screen.
Oh, can I?
It's definitely going to be the math review
Okay.
problems then.
I think it was the math review problems that doesn't, yeah.
Okay.
Yeah, we were doing the wrong one.
Oh shit. Okay.
So we're doing the wrong ones, or they were doing? the
No,
wrong-
we're doing the wrong
We're
ones.
doing.
Yeah,
No, we're doing chapter 2.
No, he said the
First 6 circles.
for 6 circles, which is on the other sheet.
Yeah, on chapter 2, it's like the third circle's like computer exercises C1.
this one. These 3 and these 3.
Yeah. Yeah, we were doing
Oh yeah, we were doing the wrong one.
Yeah.
That's tough.
Okay, now you know. Sorry.
No worries. All right, so we're all looking at the right one now.
Yeah.
You guys know you should be doing these 3 and these 3, okay?
Wait, which ones?
These 3 and these 3.
Can't even really see your screen that much. I only see like half of a question, to be honest with you.
Yeah, it's like super zoomed in.
Really?
It wasn't really working out there, to be honest with you. I just had like half a question and the start of another question.
So what do I need to do? Make it go?
Maybe like zoom out or something.
Is that on the chapter 2 worksheet?
Chapter 2.
Okay.
Can you see it now?
Nothing really changed on the screen, to be honest with you.
You guys have pulled it up on your own computers, right?
The
Yeah.
the questions we pulled up weren't the same as the one that you're showing, I don't think. Ours was like it was like a log question talking about like the distance with houses.
What?
That
Yeah, it's not the same as
chapter
someone.
2.
Yeah, I don't think these are the same questions.
Oh, no. This
From
is
chapter 2
math,
problems.
math review problems.
Okay.
You see it? Math review problems?
Yeah.
That's the one we're doing, man. Okay.
And which numbers?
The first 6 circled numbers.
Okay.
Doesn't make any sense, Alex?
Yeah.
Yeah, all good. All good, yeah.
Okay. See you in a minute.
Thank you.
Do you guys know what you're doing? These are the math review problems on Moodle, right?
Yeah, the B, C, and D, right? Like the circled ones.
Yeah, the first 6 circled problems. Right? We all on the same page?
Yeah.
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 Do you guys know what you're doing?
Nope. No clue.
No.
No.
On Moodle, it's math review problems.
Yeah, we're on that. The numbers are faded out though, so we don't know which one.
Do the first 6 circles.
Oh, we thought you said 6 or 7.
Well, they are 6 or 7, but the 6 or 7 doesn't show.
Oh, okay. All right. We'll work on it.
Okay. Well, that was a mess, huh?
Just a little bit.
So how did anybody do on that first sigma one?
Is it 80?
80. Very good. Does everybody see how that's done?
You just plugged in 2 for J and until you got to 5, right?
Yeah.
Okay.
Yeah. So it's 2 squared plus 2 plus 3 plus 3 squared plus 3 plus 3 plus 4 squared plus 3 plus 4 plus 3 plus 5 squared plus 5 plus 3. How about the next one? So the sum as I runs from 1 to 4 of x will then equal to 4 and x equal to 3.
Wouldn't that just be 12?
Just 12, right? 3 plus 3 plus 3 plus 3. How about pi of as j runs from 1 to 3 of x with x equal to 2? Two
That
times
8.
2 times 2 is 8, exactly. How about these equations of the line? Write the equation for each of the following. The gradient is a half, and it crosses the x-axis at 3.
I got y equals x over 2 minus 1.5.
But 1.5x? So this needs to be in the format of y is equal to a plus bx, right? So what would that be in that format?
Y equals 1/2 x plus 3.
Okay. Let me show you. Freaking hell. This is absolutely. I did it and I took a picture. Can you see my screen?
Yeah.
Yeah.
Gradient is equal to 1/2, crosses x-axis at 3. Must be in this format, right? Y is equal to a plus bx. Crosses the x-axis at 3. So we need to solve for a if y were 0 and x is 3. So make y 0 and x 3. We know the gradient is 1/2. So we solve for a, we have a is equal to -3/2. Plug that in, we have y is equal to -3/2 plus 1/2 x. Okay? The next one says the intercept is 2, passing through the point 3, 1. Right? So we want this equation. Solve for a is equal to 2, x is equal to 3, and y is equal to 1. Yeah, because they're giving us the intercept and the xy point. So 1 is equal to 2 plus b times 3. B must be -1/3. Therefore, this equation of the line must be y is equal to 2 minus 1/3 x. Here's almost the same thing. The gradient is 4. Here they give us the gradient, but not the intercept. So the gradient is 4 passing through -2, -2. So we know that b is equal to 4, x is equal to -2, y is equal to -2. Plug that in. -2 is equal to a plus 4 times -2.
Yep.
A must be 6. So our equation of the line is that y is equal to 6 plus 4x. Does that help?
Yeah, thank you.
How many had it? How many have learned this? It's just long gone. So you've seen this before. It's just a matter of refreshing your memory, right? Well, it's going to be important. Much of what we do is a regression and lines. When we come back Thursday, so these questions here, differentiate the following functions. We'll do those, but I'm not that mad keen on that. We'll do these, but I'm not that mad keen on that. This stuff I'm very interested in. Matrices, which pairs can be validly multiplied together? Calculate 2a, 3b, 1/2 d. Calculate the inverse of a matrix. Okay. And just a sec. Fuck, I'm having a brain fart. Oh. So these are derivatives. I don't care about matrices. This is the part that's important, matrices. Okay. Naturally, somebody asked for me to post that work on Moodle. I'll put it up there. The other alternative is to watch the video of the class and just zoom ahead to the section where it's there. But it'd be easier if it was on Moodle, right? All right, everybody. Have we had enough torture for today? If anybody wants to make me happy, they should come to class with a joke.
I got one.
Oh, yeah?
Yeah. What's the difference between weather and climate?
Well, I don't know.
You can't weather a tree, but you can climb it.
All right. On that note, I think we should call it a day.
Sounds good.
Thank you, Matt. That was very good. Thank you,
Very good.
everybody. See you Thursday.
Thanks, Professor.
Have a good one.
Thank you.
Thank you.
Thank you.
Thank you. Have a good one.
Here's my-